Hello everyone. We are now going to begin our lecture on the topic of the sampling distribution of the sample mean. Now this is the final chapter before we go on to actually performing inferential work in statistics. Now previously we had talked about the distribution of the different values of a variable that we were studying. In this chapter, however, we are going to talk about the distribution of the sample mean. And by distribution, we mean whether the different values are normally distributed, or if it's a right skewed distribution or it's a left skewed distribution. However, this time we are not looking at the individual values of a variable. The values that we are going to look at are going to be the sample mean values. Now, where do we get so many sample mean values from? Recall that we said previously that it's not possible to work with an entire population, so we draw samples from the population. And let's say theoretically it were possible to draw all different combinations of a sample of a certain size from the population. In that case, we would have a whole lot of samples, correct? Sample 1, sample 2, sample 3, sample 4. It could be a whole lot of samples based on the population size and the sample size. Now, if somebody were to go ahead and work with every sample that could be drawn from a population. So if we had all these samples, sample 1, sample 2, sample 3, sample 4, sample 5, and let's say they did descriptive studies on each and every one of these samples and came up with an X bar sub 1, a sample mean associated with sample 1, and then another sample mean associated with sample 2. So we would have so many or as many sample means as there are samples, correct? So what we are going to study now is how the sample means from the different samples are distributed, right? Now this chapter is significant because it's going to give us some facts, some theories, some formulas which we are going to apply to perform our inferential studies, right? So even though this chapter is a little bit theoretical, it is very useful in the process of performing inferential work. Now the topics that we are going to talk about in this video, in this lecture rather, are first of all the sampling error. We need to understand what a sampling error is. And we did talk about this in one of the earliest chapters, but we will have to review that one more time. And the need for sampling distribution, mean of the sample means. All right, so this is a very important concept, and also it is a theorem that comes out from studying the sampling distribution of sample means, mean of the sample means, and then the standard deviation of the sample means. So what do we understand by sampling error? Sampling error, as it says here, is the error resulting from using a sample to estimate a population characteristic. We all know by now that it's not possible, it's not feasible to work with the entire population, so we end up working with a small subset of the population, which is called a sample. And the fact that the sample contains far fewer values than the population, it is expected, it is natural that there will be a difference in the measurements between the population mean and the sample mean, between the population metric and the sample metrics. And that difference, which is just natural to happen because we are working with a very small subset of the population, we are not including a large portion of the values of the population in our sample study. That difference between the two metrics is referred to as a sampling error. A sampling error occurs due to the differences in measurements between sample data and the actual population data that occur as a result of using a sample instead of the entire population. Right? So here we have an example. We have about 6 values in the entire population. This is a very simplistic example. And we calculate the population mean, which is 15.5. And then we create 2 samples of size 3. So we randomly pick 3 values and create 2 different samples here. The first one has values 8, 10, and 13 drawn from the population, and we calculate its mean, and that's 10.333. Whereas for sample 2, we get another set of 3 different values, 13, 17, and 25. And when we calculate the mean, we get a value of 18.333. So first of all, there's not only a difference between the means, the 2 sample means here, but there is a difference between what the population mean is, which took into account all the values in the population, versus the sample mean, which worked with only 3 values from the population. So that difference between the population mean and the sample means is referred to as a sampling error, right? Now we are going to talk about the sampling distribution of the sample mean. Now in this lecture, throughout this lecture and throughout this chapter, we are going to deal with what's called the sample mean. And it's not just one sample mean, but it is a whole set of sample means. So here we have a population, let's say we have a population, and from that population we create different samples of a certain size. All right, so we have the entire population out there, and let's say theoretically we create all possible samples of a certain size. We have to decide on a size for the sample, and we create all possible samples, not just 2 or 3 or 7 or 100, but as many samples are possible to be drawn of that size from the population. So we will have sample 1, sample 2, so let's just label it as sample 2, sample 3, sample 4, and so on. All right, and it'll keep going until all possible combinations of samples are obtained from the population. All right, let's say this is sample 1. And we perform our descriptive study on each and every sample. And we will therefore come up with different sample means, right? So there'll be X bar sub 1, sample mean of sample 1, sample mean of sample 2, sample mean of sample 3, sample mean of sample 4, and so on, correct? Sample 5, and so on. And now, what we will be studying here is how the different sample means are distributed, whether they are normally distributed or whether they are skewed on one side, whether it's a right skewed distribution or a left skewed distribution. That's what we are going to study in this chapter and in this lecture. That's what we are going to talk about. Now, always keep in mind, do not forget, here we are talking about the distribution of the sample mean. Therefore, our whole set of values, the whole set is going to be comprised of different sample means. Previously, we just dealt with individual observations. We had x sub 1, not x bar sub 1, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and we calculated the sample mean of all these values and came up with a single sample mean, right? Here, each of these samples are going to have its own x sub 1, x sub 2, so we are going to end up with so many samples. And once we create all these or derive or calculate all these sample means, we no longer deal with these individual values, but we are just studying how the sample means are distributed. All right, so that's going to be the topic of study. It's all the time you will be hearing sample mean. All right, we are going to talk about the mean of the sample mean. We are going to be talking about the mean of the standard deviation of the sample means. All right, so we'll go into more detail pretty soon in some of the next slides. Now let's talk about the sampling distribution with an example. Here we have a population data of the height of 5 players. So again, this is a very simplistic example. The population size is just 5 players. And here we have listed their heights in inches, 76, 78, 79, 81, and 86. That's the entire population. And we calculate the population mean and it evaluates to 80. So mu equals 80. All right, so this entire set represents the population. Now we obtain samples of size 2 from this population size of 5. All right, so all possible combinations of size 2 that can be obtained from this population. So you can use your tree method that you had learned before when we were doing probability and even before. Remember, we spoke about how to come up with all possible combinations of a certain size from a set of values. You can follow the same tree method and it'll be A, B, A, C, A, D, A, E. So these are all the combinations of size 2 obtained from this population, and we have a total of 10 samples here. All right, so that's all possible samples. All right, if you shouldn't miss out one, even one. All right, all possible samples should be included, and this is the entire sample set obtained from the population here. And then we look at their height. So A has a height of 76, B has a height of 78. We find the mean. 76 plus 78 divided by 2 is 77. So there's X bar being calculated in the third column, and here we have an X bar value for every sample. All right, so we have here X bar sub 1, X bar sub 2, X bar sub 3, and so on, all the way to X bar sub 10. Okay, so we have so many of these X bars values, the sample mean values, and then what we can do is we have to study the distribution, of course, of how these mean values are distributed, and then we will compare how the mean of all these sample means compare with the population mean. All right, and that is going to be a very important finding. It will give us a very important fact about the distribution of the sample means, which we are going to use in solving various problems, all right, especially in inferential studies. So I will ask you to pause the video here and calculate the mean of all these sample means, right? And I'm going to write here. All right, so you may want to pause the video shortly and calculate the mean of all the possible means. So mean of all possible means, and this is how it's written, all right, mu with a subscript of x bar, which reads as mean of all the sample means, equals, you have to sum up all these x bar values and divide by 10. There are 10 of them. You have to divide same sigma x divided by n formula, the formula for the mean, and just pause and calculate this value and come back and restart the video again and see what value you got. All right, so you should have come up with a value of 80. All right, so when you found the mean of all the sample means, that should be a value of 50. That should calculate to 80, not 80, right? So when you compare this mean of all the population means with the population mean that we calculated for the entire population, they are equal. All right, and that equality is not only true for sample sizes of 2, it will be true for any sample size out there. If we had created samples of size 3 and we calculated the mean of all the sample means, it would still come out as 80. If you had chosen sample sizes of 4, found the respective x bar values, and found the mean of all those sample means, just the way you calculate it here, you would have come up with a value of 80. If your sample size was 1, you would still have come up with the mean of all the sample means would have been 80. All right, and this is true for any sample size, any population size. All right, this results in a very important fact, in fact, a theorem of the sampling distribution of the sample means, that the mean of all sample means will be equal to the population mean, right? And we are going to use this important fact in solving problems related to sampling distribution of sample means, right? Now, so far we have learned that the mean of all the sample means, the mean of all the sample means is equal to the population mean. That's an established fact, all right? No matter what your sample size is, whether it's a size of 2 or 3 or 5 or 100 or 1000, the mean, if you take the mean of all possible sample means from your population study, samples drawn from your population study, and find their means, the mean of all the sample means will always be equal to the population mean. Okay, now here we are going to see how much the different sample means deviate from the mean of all the sample means or the population mean. All right, so we have 5 different figures, dot plots shown here, and all of them have the x bar. Again, we are talking about sample means at this point. All right, all these dots refer to the values of sample means. So as we see over here, this dashed line going up is the mean of all the sample means, or also called the population mean. All right, and that was 80, correct? It was the mean of all the sample means. And now we see how much the individual sample means are off from the mean. all right, from the mean of all the sample means. And all these figures, these 5 figures here, are for the different sample sizes. The first one on top is when the sample size n is equal to 1. Then we have n equals 2, 3, and then the last one is n equals 5. And look at the spread of the sample means. When n equals 1, we see that the sample means are quite widely spread, isn't it? All right. And then we have look at the spread when the sample size equals 2. We see that it's a little bit closer than what it was when n equals 1. So when the sample size was increased a little bit, the sampling error, or in other words, the spread of the sample means, is little bit less than what it was when n was equal to 1. Look at n equals 3. We've now increased the sample size even more, and we see that now the spread has become closer, is getting closer to the population mean, or the mean of all the sample means. And then n equals 4 is even closer, and when n equals 5, which was the population size as well, when the sample size becomes equal to the population size, the mean is the mean of all the sample means, or rather the sample mean, is exactly the same as the mean of all the sample means. Right? So what we learn over here, what we learn from here rather, that as we increase the sample size, the standard deviation, the deviation of the sample means, get closer and closer to the population mean. So, and that's again a very important rule that we will have to remember and apply when we go on to inferential studies. All right. So the standard deviation, the deviation or the standard deviation of the sample mean, all right, it decreases as the sample size increases. Sample size increases, as we saw in these various dot plots shown here, where the sample mean, or as the sample mean was increasing, the deviation of the sample means was decreasing, was getting closer and closer to the mean, to the population mean, right? So while the mean of all the sample means is equal to the population mean, the standard deviation of all the sample means will be influenced by your sample size. So in the formula for the standard deviation, you will see n being used to calculate sigma. All right, because n has an influence, the sample size has an influence on the standard deviation. Now this table here charts the sampling distribution and the error, the standard error for, or the sampling error, not standard error, sampling error for different sampling sizes, using the same example on heights, right? So over here in the first column, we have the sample size n listed as 1, 2, 3, 4, 5, then number of possible samples. So when the sample size is 1, then the number of possible samples is 5. All right. So if we take all possible samples from a population size of 5 and create samples of size 1, n equals 1, then the number of possible samples is 5. When it's 2, when the sample size is 2 out of 5 population size. Then the number of possible samples was 10, as we saw when we created in one of the slides. If you go back and watch, it'll show that we had 10 different samples, all right, and that comprised all possible samples of size 2 from a population size of 5, right? So that's the number of possible samples. For sample size 3, it was 10 as well. It is 10. We didn't work that out, but it will be 10. And then when the sample size is 4, number of possible samples will be 5, and when the sample size is 5, it'll be 1. Now they are looking at the number of sample means that were within 1 inch of the population mean. So when the sample size was 1, there were 2 sample means which were within 1 inch of the 80 inch, which was the mu, right? Mu of the mean of all the sample means was equal to 80 inch for our example. And we had 2 observations that were within 1 inch, which is 40% of the observations. And there were 0 observations which were within ½ inch, plus minus ½ inch of mu. Percentage within 0.5 inch of mu was 0%. So that's what this distribution shows. When it was when the sample size was increased to 2, you see the percentage within 1 inch was 30%, then 50%, 80%, 100%, and percentage within 0.5, that means ½ inch of mu, keeps increasing as the sample size increases, right? That's all that this chart is showing us. Now let's look at the relationship between sample size and sampling error, or the standard deviation. When we work with samples, we also refer to the standard deviation as the sampling error. So the larger the sample size, the smaller the sampling error tends to be in estimating a population mean mu by a sample mean x bar. So the larger as the sample size increases, the standard deviation decreases. The sampling error gets closer and closer to the population mean. The sampling error gets smaller in estimating a population mean mu by a sample mean, which is denoted as x bar. We are back at that example on heights now. Again, it's the same table. We created samples of size 2, n equals 2. All possible combinations of size 2 that we can create out of a population of 5, A, B, C, D, E were the values in the population, correct? And the mean of the sample mean, as stated here, says for samples of size n, the mean of the variable sample mean x bar equals the mean of the variable under consideration. In symbols, it's mu sub x bar equals mu. That means the mean of all sample means will be equal to the population mean. That's kind of an established fact. It's like a theorem. So when they ask you to find the mean of all sample means or to estimate the population mean, then all you do is you sum up all your x bar values and then divide by the number of samples, all right? And that will give you the mean of all the sample means, and which will be equal to the population mean. So if you're given all possible sample means values, then and they ask you to estimate the population mean, then whatever the mean of all the sample mean equals to will be the population mean will equal the population mean. Likewise, if they give you the population mean, then doesn't matter what the sample size is. It could be 2, it could be 3, it could be 1, it could be 20, it could be anything. Uh, doesn't matter. Regardless of what the sample size is, the mean of all the sample means will be equal to population mean. All right. Now, later on, we will be doing some worksheet. I'll go over some worksheets on this chapter, and it's going to supplement. So there'll be exercises there to show demonstrating how we should work on the problems on this chapter. So make sure that you kind of watch that too after you watch the lecture. All right, because there are not any practice problems in the lecture as such, but you will need to go through the worksheet because this is mainly a theoretical topic. I have kept this separate from the worksheets. All right. Now we look at the standard deviation of the sample mean and the associated formula that goes with it. It says here for samples of size n, the standard deviation of the variable x bar, which is the sample mean, equals the standard deviation of the variable under consideration. In this case, that's the population mean, divided by the square root of the sample size. In symbols, we write the standard deviation, that sigma sub x bar, which is read as the standard deviation of all sample means, is equal to the population standard deviation divided by square root over n. We have to factor in the sample size in the calculation because, as we have seen, that the standard deviation of sample means is influenced by the sample size. As sample size increases, correct, we saw that as sample size as n increases, the standard deviation decreases. Therefore, there's a relationship between the sample size and the standard deviation of sample means. And therefore, we have to factor in the sample size into the calculation. Now, I might as well mention at this point is that previously when we were finding z-scores, right, when we were calculating z-scores of observations, we had the formula x minus mu over sigma, right? When we go to calculate the z value for sample means, all right, when our individual observations are sample means instead of just values, individual values, when we are working with sample means, the formula is going to look like this. X bar, right? Instead of x, we are going to have x bar minus mu divided by, we have to use the formula for the standard deviation of sample means. So it's going to be in the denominator, it's going to be sigma divided by square root over n. So the formula for the z value is going to change a little bit from what we were using previously. Whenever we work with sample means, it's going to be x bar. That means sample means represent the individual observations, right? So x bar minus mu over sigma divided by square root over n. Now let's look at the sampling distribution of the sampling mean. Now there are three components to a sampling distribution. One is, when we talk about the sampling distribution, we talk about the mean, we talk about the standard deviation, and we describe the distribution, right? And that's going to be throughout, all right, for any for any study, when we talk about the sampling distribution, we have to talk in terms of the mean, the standard deviation, and then the distribution, describe the distribution. So first, let's read through the verbiage in this slide. It says, suppose that a variable x of a population is normally distributed with mean mu and standard deviation sigma, then for samples of size n, the variable x bar, which is the sample mean, is also normally distributed and has a mean of mu and a standard deviation of sigma divided by square root over n. So when it says the variable of a population is normally distributed, that means that refers to the variable that we are studying. Certain variables are known to be normally distributed. For example, heights, normally distributed. IQs are normally distributed. So if we know what the variable that we are studying, whether it's IQs or heights or anything else, if we know it's normally distributed, then we can be pretty sure that the sampling distribution of the sample means will also be normally distributed, and it'll have a mean of the population mean, because we just saw that the mean of all sample means is equal to the population mean, and the standard deviation will use the formula sigma divided by square root over n, because we just saw previously that the standard deviation of sample means gets influenced by the sample size. Here's an example showing the normal distribution of sample means of IQs. IQs, as I said before, are known to be normally distributed. The variable IQs are known to be normally distributed. So let's look at these different figures here and try to understand the distributions. The first figure here is for the population mean and the population standard deviation. The population mean of IQs is believed to be 100, and the standard deviation is 16. All right, so this is a graph. This is the distribution of IQs, a normal curve of IQs for the entire population, with 100, the mean being at the center. Now, look at the subsequent figures. In the second figure, the standard deviation is 8. All right, so the second figure has a sample size of 4. The figure A, the first one, was based on the entire population. The second one, figure B, is based on a sample size of 4. And the standard deviation is 8, and the mean is 100. So how did they come up with 8? Of course, the mean of all sample means is equal to the population mean. That's an established fact, correct? Therefore, doesn't matter what the sample size is, the mean is going to be 100, and therefore they have a 100 for the mean of this curve. How about the standard deviation? Is it the same as the population standard deviation? Absolutely not, because the standard deviation will be influenced by the value of the sample size. And the formula for the standard deviation is population standard deviation over x. So we have to take the population standard deviation value, which in this case is 16. Sorry, I made a mistake here. Let me fix that right away. It's not x, it's square root over n. All right, square root over n. So 16 divided by n is 4. for this particular figure. So we will have square root over 4, which is 16 divided by 2 equals 8. And that's why they have 8 for the standard deviation. So when the sample size is 4, the mean still stays the same as the population mean. However, the standard deviation is 16 divided by the square root of n, which in this case is 4, which gives us a value of 8. And as you see that since the standard deviation value is less than the population mean, less than the population standard deviation, the curve is a much narrower curve than the population curve. Right? Let's look at the final figure here in figure C. This time n equals 16. Let's look at the mean. Then this how the shape of the normal curve is. It's still a symmetrical bell-shaped curve, but it's a tall and narrow curve. The population mean is still 100, whatever the population mean is, right? The mean of all the sample means is still equal to the population mean. No change there. Irrespective of what the value of n is, the mean does not get affected by the sample size. Please keep that in mind. However, the standard deviation value for when n equals 16 will be calculated using the formula sigma divided by square root over n. So population standard deviation is 16 divided by square root over 16, which is 16 divided by 4, which is a 4, and that's the value they have here. And the smaller the standard deviation, the narrower and taller is the graph, right? Is the curve. Now we come to a very important theorem in statistics called the central limit theorem, which guides a lot of the inferential studies. The central limit theorem, or CLT for short, states that for a relatively large sample size, the variable x bar is approximately normally distributed regardless of the distribution of the variable under consideration. The approximation becomes better with increasing sample size. So what this essentially means is if we can use a fairly large sample size for our study, then even if the variable may not be normally distributed, we can be pretty sure that the distribution of the sample mean is going to be close to a normal distribution, is approximately a normal distribution. And the larger the sample size we use, the closer it is going to be to a normal distribution. So, in other words, regardless of how the variable that we are studying is distributed in real life, if we use a large enough sample for our study, we can be pretty certain that the distribution of the sample means of that variable is going to be normally distributed. Here's a graphical representation of the central limit theorem. We have 3 columns here. In the first one, shows the distribution of the variable. So distribution of the variable in this case, in the first column, the first picture is normal, correct? It is a symmetrical normal curve, bell curve. When we use a sample size of 2, this is how the curve looks like. It's still bell-shaped, it's still normal distribution, and as the value of n, the sample size increases, the graphs get taller and narrower. When it grows all the way to 30, when sample size increases to 30, it becomes a pretty tall but very narrow rise of the curve. So here the variable in the first picture, first column, the variable was normally distributed. In the second column, we look at a distribution to start with. The variable is definitely not normally distributed. It is a reverse J curve, correct? However, and that's how its distribution is for the population. When we look at the sampling distribution with the sample size of 2, you see how this reverse J-shaped curve has taken the shape of a normal curve. It doesn't look normal, it's not symmetrical, it is right skewed definitely at this point. However, as we keep increasing the sample size values from 2 to 10 to 30, look at how the curves look like. It's getting closer and closer towards a normal distribution. This shape is pretty similar to the shape of the curve if the distribution of the variable was normal. All right, it's pretty much this curve looks similar to the curve in figure A, right? When n is 30, when the sample size is 30. And then in the last column, we have a uniform distribution. So if a variable has a uniform distribution, then as we increase the sample size, look at how the distribution changes. When n equals 2, it's a kind of a triangular shape, triangular distribution. When n equals 10, it becomes a smooth curve. All right, that the triangle shape has now become a smooth curve. And then when n is increased further from 10 to 30, the curve looks very similar to what the curve of a normally distributed variable is. All right, so that's what the central limit theorem states. Sampling distributions of the sample mean for normal, for reverse J, and uniformly distributed variables. As we increase the sample size, when we use large sample sizes for our study, we can pretty much assume that the distribution of the sampling means is going to be normally distributed, even though the variable may not have been normally distributed to start with. Finally, let's summarize the sampling distribution of the sample mean. It just summarizes whatever we discussed in this lecture so far. Suppose that a variable x of a population has mean, mu, and standard deviation sigma. Then for samples of size n, the mean of x bar, in other words, mean of all the sample means, equals the population mean, or mu sub x bar equals mu in notation form. The standard deviation of x bar, that means the standard deviation of all sample means, equals the population standard deviation divided by the square root of the sample size. So sigma sub x bar equals sigma divided by square root over n. If x is normally distributed, so is x bar. So if the variable under consideration under study is normally distributed to begin with, then the distribution of the sample means will also be normally distributed regardless of sample size. However, if the distribution of the variable is not normally distributed, but we use a large sample size, then the sample mean is distributed normally, approximately normally, regardless of the distribution of x. All right, so that brings this chapter to an end. We will now go into performing actual inferential studies in the next couple of chapters. Now, we didn't work through any exercises for this chapter, but I want to reiterate that there are worksheets, and I will post worksheet solutions, video solutions showing you how to work through the problems for this chapter. Please watch those, all right? Otherwise, you will not be able, just because this lecture was essentially very theoretical, you will need to see the practical side of it, how all these facts and theories are applied in solving problems. And for that, please watch the worksheet solutions for this chapter. All right.